Morning students, today we are going to see the basic problems using Smith chart. Before we are going to the Smith chart, let me give some brief introduction about Smith chart. The Smith chart is the polar plot of reflection coefficient. I hope you know the meaning of reflection coefficient, right? So that is the ratio between reflected voltage to the incident voltage. That happens because of ZR is not equal to Z0, right? Okay, so as we know, the reflection coefficient value tau ranges from -1 to 1. When I am taking the magnitude of this value, it will become 0 to 1. Similarly, when I am taking the phase, that ranges from 0 degree to 180 degree, right? So Smith chart is nothing but it is constructed by a unit circle whose radiuses are ranging from reflection coefficient values between 0 to 1, right? So Smith chart is constructed by a unit circle with the reflection coefficient values ranges from 0 to 1. Then why do we need Smith chart? See, in unit 2 we have solved ZS and ZR using numerical formulas, right? However, to avoid the tedious computations involved in computing the ZS and ZR, there have been some of the graphical approaches are developed, right? So one such approach is nothing but Smith chart, right? So though there are multiple graphical approaches have been there, one such approach is Smith chart. Okay, so and here in Smith chart, whatever the Smith charts that we are using in our academics or in our particular subject, those are all normalized Smith chart. That means, see, in typically the Z0 values are ranging from 50 ohms, 100 ohms, 75 ohms, right? So instead of having different Smith chart for each of these characteristics impedance, we are going to prepare only one Smith chart for any of the transmission line, right? So that can be achieved by the procedure called normalization, right? So that is what the meaning of normalized Smith chart, right? So whatever the load impedance value is given, whatever the characteristics impedance is given, right? So with respect to the characteristics impedance, Z0, the ZR has to be normalized. That is small ZR equal to capital ZR. That is our load impedance. That has to be normalized by the characteristics impedance ZR. Right. So this is what the meaning of normalization. Right. This is a typical Smith chart. Before going to the Smith chart, let me explain each and every term. Okay. So for that, first we should understand what do you mean by impedance, right? So we know that the impedance is constructed with respect to two things. One is R, another one is X. What do you mean by R? R is nothing but the resistance. What about X? X is nothing but reactance, right? And here this X reactance, if it is positive, then it is nothing but the inductance. If X is negative, then we can represent that by capacitance, right? So this we should know. And the second thing is that we should also aware about Y. What do you mean by Y? Y is nothing but admittance. Y equal to what? G plus JB, right? So what do you mean by G? What do you mean by J? B. So G is nothing but the conductance. What about B? B is nothing but susceptance, right? So this susceptance imaginary value, if it is positive, then we will be representing that by capacitance. If it is negative, then we will be representing by inductance, right? So this we should aware before we are going to the Smith chart. Okay. So now we can see here. Now in this Smith chart, if you are considering the Smith chart as impedance chart or Z chart, right? So you can, if you are considering the Smith chart as Z chart, right? Z chart, then the real value and imaginary values are going to be resistance component and reactance component. Please look at here, all of you please look at. So here we can see that this is resistance component R by Z0, and here we can see that inductive reactance component. Why it is inductive reactance is that here the values are positive, right? So that's why it is called positive reactance component or inductive reactance component. And below this real axis, this value here we can read it out capacitive reactance component. So here the value is negative, reactance value is negative. So that's why it is called capacitive reactance. When you are considering the Smith chart as a Z chart, this real value, this is nothing but the real axis. Okay, this is nothing but the real axis. Above, this is real axis or resistance component. Above the real axis is positive component, positive reactance, that is inductive reactance component. Below the real axis is negative reactance component or capacitive reactance component. The same Smith chart, if you are considering as a Y chart, if you are considering the same Smith chart as Y chart means admittance chart, then the value of a real part will be conductance component, not the resistance component. Similarly, the value of imaginary positive susceptance values are going to be capacitive susceptance, and the negative susceptance are going to be the inductive susceptance value, right? So these things you should be familiar, right? And here, as I told you, the Smith chart is constructed by resistance circle and reactance circle. Here we can see that this circle, right? So kindly trace this circle, right? So let me change the color. So kindly trace this circle. See, if you are tracing the circle, so where it will end? Definitely, it is going to end at this place, right? So you can trace it. So definitely, it is going to end at this place, right? Similarly, wherever if you are tracing the circle, right? Wherever if you are tracing the circle, definitely it will go to end at what? A rightmost part of a Smith chart, right? So now here you should understand one primary thing, that is here the value of the resistance R equal to 0, here the value of resistance R equal to infinity, right? So in between you can see that R equal to 0, R equal to 0.1, 0.2, 0.3, 0.4, 0.5, like that the values are varying 1, 1.2, 2, 2.2, 3, 4, 5, 10, up to the value goes to up to infinity. So this is nothing but the resistance circle. Similarly, here we can see that here we can see that one more circle, right? So this circle, please look at here, this circle, all of you please look at, so the one which I am going to indicate in blue color, right? So you can see, so that also where it goes to, it goes where it goes, again it goes the rightmost part of a Smith chart, right? So here also the values, so here we can see in interior 0 0.1, 0 0.2, 0 0.3, 0 0.4, 5, 6, 7, 8, 9, 10, sorry 1, right? 1.2, like that you can see 3, 4, 5, 10, up to the value is infinity. So that means the reactance value here x equal to 0, here the value of what, x equal to infinity, right? So the one which is going this way, the one which I am indicated in this blue color, that is nothing but the reactance circle. The one which I am indicating in this color, right, that is nothing but the resistance circle, right? So this is how the Smith chart is constructed. I hope you know the meaning of it, right? So let me give some example, right? So that it is easy. So if somebody asks you to plot the value, that is small zr equal to, that is 0.4 plus j 0.8. That means what you have to do? 0.4 is the real value, 0.4 is the 8 is the imaginary value, right? So you have to look at 0.4 and you have to trace 0.8, where the value is 0.8, 1, 2, 3. So this is 0.8. So what you have to do? So now you try to trace it, the value like this. Okay. So now you have to trace it. Now you try to trace the real value also like this. Okay. So now both the points are intersecting at one place, right? So this is the point. Now we have to mark with dot under the end circle, right? So this is nothing but the small zr. Similarly, if somebody asks you to plot the value small zr equal to 1.2 minus j 0.8, what you have to do? See, 1.2 is the real value minus 0.8. That means 1.2 you have to take here. Since the value is minus, you try to trace the minus 0.8 at the where? You have to take it at the negative imaginary axis. You know which one is negative imaginary axis. So this is the negative imaginary axis and this is 1.2. So both the values are intersecting at this point. So this is nothing but my small zr, right? So this is how we have to trace the value of zr. Okay, fine. In addition, see the here there are 4 peripheries are available in Smith chart. In the outer side there are 4 peripheries are available. So let me explain it over here. The outer, the outside this Smith chart there are 4 peripheries are available, right? So the innermost one are nothing but the reactance component, inductive reactance component or capacitive susceptance, reactance or susceptance component, right? So the next to the interior, the next value is called angle of reflection coefficient, angle of reflection coefficient tau. And the next scale is nothing but wavelength towards load, right? WTL means wavelength towards load. And here this scale is nothing but wavelength towards generator, right? So this is the four scales are available in the Smith chart, right? So the one which you are writing the interior part of the Smith chart useful to find the small ZR value, right? And the next one is angle of tau. We know that the angle of tau, so we the reactance values are ranges from 0 to 0 up to what? Infinity. The angle of tau that starts from here. Angle of tau starts from 0 degree and ends at where? 180 degree. Right? So 0, 10, 20, 30, likewise it will vary 30, 40, 50, right? So likewise the values are varying up to some infinity. Similarly 0 here, what? Minus 10, minus 20, right? So similarly here minus 170 is there. Okay, so this is the typical scale used for finding the angular reflection coefficient, right? So the next one is wavelength towards generator and wavelength towards load. That is very easy. Please look at here. So here in the Smith chart, you can see that this is 0, and after that here we can see that 0.1. Here we can see 0.01. After this 0.02, right? So you can able to see in your Smith chart like this, right? So here the value is 0.12. Here the value is 0.13, right? Here we can see that 0.25, right? Similarly, the value is 0.3, right? For time being, let me mark it the important value. So 0.4 and here 0.49. After this, here the value is again what? 0.5, right? So remember, guys, in Smith chart, the wavelength is varying from, you know, right? So the one complete revolution of the Smith chart equivalent to how many degrees? One complete revolution of the Smith chart is equivalent to how many degrees? Yes. Yes, obviously it is equal to 360 degree, right? So one, if you want to travel one complete Smith chart, right? So 360 degree, that 360 degree equal to lambda by 2, right? So if you want to completely travel one revolution, right? So that will take 0.5 lambda, right? So that is what the inference. That means if you want to travel semicircle, then it will take what? 0.25 lambda. If you want to travel entire Smith chart, then it is 0.5. See, if you want to travel 1 lambda means what you have to do? First you have to complete one revolution, then you can go for one more revolution for one lambda, right? So this is what the meaning of wavelength towards generator. Similarly, wavelength towards generator means this scale will varies like in clockwise direction, but this WDG scale here you can see that this is 0 and here we have the value here we get 0 and here the value is 0 0.1, 0 0.2, sorry 0 0.01, 0 0.02, 0. You can able to see in your picture, right? 0 0.03, 0 0.25, here 0 0.26, right? 0 0.25, 0. Sorry, this one, sorry, this is 0.26 and this is 0.27. Likewise here we can see the 0.4, 0. This is 0.4 and this is 0.3 and this is again 0.49, right? So instead of rotating in clockwise direction, it is varying which direction? Yes, yes, it is varying in anti-clockwise direction, right? So this scale is also will be used for finding the load impedance, right? So this is the four important scales used in the Smith chart. I hope this is very clear for you, right? In addition to that, there is something called radially scaled parameter. We can see that, right? So I think this will be better. So reflection coefficient, radially scale parameter, you are going to see reflection. Okay, here we are going to see the value called what? Reflection coefficient, right? So you can see that reflection, right? So here VOL, here what? REFL, reflection coefficient, this is VOL and this is what? PWR. We know that this is your center point. You know the values of reflection coefficients varying from 0 to what? 1 magnitude. So 0, what is the next value? 0 0.1, 0 0.2, 0 0.3. So this 0 0.4, 0 0.5 up to 1. Similarly, this is VSWR, right? So here we can see that this scale, we can see that this is standing waves and VOL means voltage standing wave. Here we have current standing wave also, but we are not going to measure it, right? So this is voltage standing wave ratio. So here this scale you have to use. Here we can see that what is the typical VSWR values or ranges from, we know that 1 to, yes, what, 1 to infinity. That's why here 1 to infinity. So here 1, 1.2, 1.4, 1.6, 1.8. So up to the values are goes to infinity, right? So the remaining parameters are not useful for you, I mean, on this particular semester. Maybe it will be useful for you in future. That is also very easy, right? So this is the basic introduction about the Smith chart.